is to understand model evaluation procedures. Because we're going to start to build machine learning models, but if we don't understand how well we're doing, i.e. bias and variance, we're not going to know if this model is going to actually work in the real world. Because theoretically, we're creating all these models to actually be used in the real world. So, what's wrong with training error? So here's a little thought experiment. Suppose we train our model using the entire data set. How low can we push the training error? By training error, I mean bias. How low can we push the error? The answer is to 0. Because we could theoretically memorize everything. If you memorize the entire training set, you can get a training error of 0. You can never be wrong. That is the definition of overfitting. Overfitting means you memorize, just to a certain extent, your entire training set, and that's essentially all you know. Now, the problem is the following. The green line curve represents overfitting. It's trying too hard to make sure that the red dots are on this side of the curve and the blue dots are on this side of the curve. It's trying really hard to make sure that that's always the case. I'm sorry? Oh, sorry, thank you. I can't talk from where I am, so I was going to draw, but I forgot. It tries really hard to make sure that red is over here and blue is over here. That's called overfitting. It's trying too hard. The black curve, while it's sometimes incorrect, this red dot is over on this black curve, this blue dot finds its way in a sea of red. This black curve seems to not be doing as well, but it's more stable. Okay, now let's try this. The green curve, which is overfitting, doesn't have a low or a high bias. The green curve. Low. Why?
Because it has a high variance.
It's not because it has a high variance, because you can have low bias, low variance. It's a low bias because it's never wrong. It always gets it right with these red and blue dots. It's always right. It has a 0 bias, in fact. It's so low it's 0. It's never wrong. But the variance is very high. If you took a random selection assortment of these dots and drew that green line again, it would have to try really hard in a completely different way. Like if I only chose, if I got rid of this red dot, took it out, what would the green curve do? If I took out this red dot, this green curve would just snap back over here. If I took out this blue dot, the green curve has no reason to be here anymore and would snap back into place. That's what leads us to have a high variance. It's because if I slightly change my training data, that green curve would drastically change as well. The black curve has a higher bias. On average, it's sometimes wrong. It will sometimes be incorrect. However, if I take out this red dot, the green curve will run away, but what will the black curve do? It won't really, you'll shrug and say, okay, I'll move slightly away from it, I guess, but not really. Because this black curve is it's this more consistent curve. Which makes the black curve have a higher bias, but a lot lower variance. The black curve doesn't change as much if I change the training data. The green curve depends very much so on the training data. Here's another example. On the left, we are underfitting the data. That line isn't doing a great job at catching everything. On the right side, we've overfit the data. It's trying way too hard to capture all of the data. And just like in the code we saw earlier, if I took out some of those points, that curve would just look entirely different. Whereas the line, if I took out some of the points, it probably wouldn't move that much. So underfitting is an example. Underfitting is a high bias, low variance, whereas overfitting is a very low bias, it's doing a good job, high variance. If I take out some of the points, the curve looks entirely different. It's inconsistent. It's unreliable. So what's wrong with training error? So if we train our model, the entire data set, we can take the training error down to 0, memorize everything, overfit it. But it's no longer a good estimate outside of your training. Which is why over here I have, above, I'll raise this for a quick second, the two main types of data when we're working with prediction is in sample and out of sample. In sample means that's the data you were given. This is what we know. This is what we would know. Out of sample data is, this hasn't happened yet. That's what we're trying to train for. So of the in sample data, what you're given, you split that up into a training and a test. Because you'll fit the model to your training and then test it on your test set. But you know the answer to all of them. In fact, it's because you know the answer that you're allowed to test it, because you can see how wrong you were. The whole point is, when you're done, out of sample data comes in. Tomorrow's stock day opens, a new mammal comes in, there's a new UFO sighting. That's out of sample data. It's data that the whole reason you made the model for was for the out of sample data. Why this matters? Because the data that you're given won't always be the end of the data stream. You'll keep gathering data, but there will always be new points that come in, i.e. new UFO sightings, new irises, new children will be born for the neonatal infection. The whole reason you're building the model is for the child that will be born tomorrow to see if they will have an infection. That's the whole point. So in the next couple of slides, we're going to talk about how do you make a model that generalizes well. So this is all about decreasing variance, making it more generalizable, making it more consistent. So we have a data set represented by this large rectangle, like a data frame. And we have that model. It could be K and N, it could be any model that we create. The first thing that we'll do is we'll split the data set. This is our in-sample data. In-sample. We'll split it. We'll call the top, the larger part, training, and the bottom we'll call it test. What we'll do is we'll keep tuning our parameters. Does KNN with 3 neighbors better, or 5 neighbors, or 7 neighbors? We'll find the best value. We'll choose the best one, as in I think 7 is the best. And then we'll train the model on all of the data. Once we've chosen the best one, now we'll do it on all of it. Because the last step is the out of sample data comes in. And now we have to try it on that. So this is development, train, test, tune, choose the best one, push it to production. Now it's working in the real world. So like Netflix will tune their parameters to say, okay, we're pretty sure our movie prediction algorithm is very good. And then tomorrow, Bob signs up and then wants movie predictions. Bob is out of sample data. Netflix did not know about Bob before. He's the reason they made the model. So how well does the error set, the test set error, predict out of sample? Because it's almost like we're treating the test set as if it were out of sample, and we are. We are pretending we don't know the answer and letting the model go, and then bringing in the answer to say, okay, how well did it do? That's tested. Well, thought experiment. What if we had split the data differently? What if the green were up here and we chose the first part as our test and the bottom half, as our training? Would there be any difference? Yes. Well, would the test error be the same? No, it would not be the same. Because it's completely different data that we're testing it on. And this is where the variance comes into play. As I choose different training, different test sets, of course that the test error is going to be different. But is it still similar to the other split? If I split it 10 different ways, are 5 of them very low error? Are 5 of them very high error? Or are they all around the same error? Is it a consistent model? That's the variance. So we can split the data in many different ways. But what if we split it in 10 different ways, took our error, and then averaged them all together? Would that be a good representation of the general error of the model? Yes. And that's called cross-validation. Here's how it works. Take data, 150 flowers, 1 million stock data, 800 UFO sightings, 100 NBA players, whatever it is. Randomly split the data set into k equal partitions. K is a very common variable. It's not the same as k nearest neighbors. It's not the same as k means clustering. K is another integer. Split it up into k equal partitions. So if k were 2, we would split Iris into 2 partitions, each with 75. If it were 5, we would split it into 5 equal partitions of 30 each. With split into k partitions, use partition 1 as the test, and all of the rest of them as training. So if we did it with Iris, with a cross-validation of 5, we would split it up into 5 equal partitions, each of them with 30. We would use the first 30 as a test, and the remaining 120 as training. We would then fit the model to the 120, test it on the 30 that it hasn't seen yet. And then you do the same thing for each of the partitions. So, if here is my data set, and I split it up into 3 partitions, on the first trial, and I'll label them 1, 2, and 3, on the first trial, number 1 will be the test. 2 plus 3 is what I'll train it on. And then, on my second trial, my number 2 will be my test, and 1 and 3, these 2, will be my train. On the third trial, I'll use the third partition as a test, and then 1 plus 2 will be the training. So I'm essentially effectively training the model k times using different training data each time. And if I have a model with low variance, I would expect that each time I do this, my error is about the same. About the same. If I have a high variance, my error is all over the place. Sometimes it does really, really well. Sometimes it's all over the place. So different models each time. And then when you do it k times, you take the average of the error and say that's your in general. On average, that is your error. So for example, with this data set, on the first trial, if I'm doing a cross-validation with 5, the red represents my training, my blue represents my test. The first trial, I'll choose these randomly blue dots, and test it on those, train it on the red. The second trial, I'll take these other blue dots as my test and the red as my training. You get the picture. Here, there's other blue dots that I haven't used yet as my test, here and here. What this does, it does a lot, what it does is, it gives you a more accurate estimate of your out-of-sample prediction error. You cannot ever know your out-of-sample prediction error. Does someone want to tell me why? Why could you never know your out-of-sample prediction error? Say it again.
It's out of sample, then you don't know what the answer is, you know, it's right or wrong.
Why not? Why not? When I have it?
Once you observe something, it's sample.
So what that means is out of samples I haven't observed it yet. Exactly. I can never know out of sample error because it hasn't happened yet. So cross-validation is the best way to predict out of sample error. We're effectively running our model several times and averaging the error. That is what we're doing. That is cross-validation. We are running the model several times and averaging the metrics. Because if you just run it once and it does really well, what if the model had a high variance? You run it again and it's completely different and it didn't do so well. Cross-validation allows us to see that and account for it. So how do we do that in code? Does the idea of cross-validation make sense? We're splitting up the data, and instead of running KNN once on all of the data, we're going to run it 5 times on the 5 separate partitions of the data, and then average the results together. What that will tell us is, on average, how well does KNN do with 3 neighbors? On average, how well does KNN do with 4 neighbors? On average, how well does KNN do with 5 neighbors? 6, 7, 8, 9, 10, so on and so forth. So I'm looking at 06 model evaluation procedures.py. We'll have our NumPy, our matplotlib. We're going to load our iris data, 9, 10, and 11, our x and our y. Our x represents what again? Our predictors. Our y is our response, same as before. Here's scikit-learn again. We're going to import the k-neighbors classifier. We're going to instantiate a new KNN model. KNN equals k-neighbors classifiers, and neighbors equals 1. We're going to fit it on everything, score on everything. We get that error, or we get that accuracy of 100%, right? Now we know why that does not work. Now we know why it's 100%. Because we're not doing cross-validation. We're not even using any train test splitting. We have to split the data into a training set and a testing set. We cannot train it on everything. Scikit-learn gives us a train test split method. How nice. We'll import it. It's called train test split. Now, to demonstrate what it does, on line 26, I create some fake features, call them features. If you look at it, it's just 0 through 9 in the first column, 10 through 19 in the second column, some fake data. And response, I just wrote even and odd 5 times. So it's just even, odd, even, odd, even, odd, even, odd, even, odd. That's all it is. The way this works is I can do features train features test equals train test split features. What does this model do, or this method do? Now look at features train. Of the features, which are 2 columns, it took 1, 2, 3, 4, 5, 6, 70% of them, 7 of them, and it called it my training data. Notice which ones it chose. It's arbitrary. It is a random 70% of your training data, of your in-sample data.
All get the same thing.
What did you say?
We all got the same things, right?
It's because earlier, remember we set the seed? Yeah, we're all getting the same numbers because we all have the same random numbers happening. And it's just so you get the same thing as me. So unless you change the seed, you're going to get the same thing as me. The test are the remaining three. So we have the 1, 3, 9, 5, 2, 7, 0. Here's the 6, 4, and the 8. So it just splits it up. It's a really fancy method that just splits up our data set into 70, 30%. And we can change whether it's 70, 30 to 80, 20, 90, 10, 50, 50. But usually we keep it a 70, 30 split. So all we've done is split the features up. What you can also do in line 40 and 41, if you hand it features and response, it will make 4 different things. So we inputted all of our features, we inputted all of our response, and it spit back 4 things. A training set for our features, a test set for our features. So here's 70% of our features. Here's the remaining 30% of our features. It also split up the response. Here's 70% of the response, and here's the remaining 30%, 3. It did it in such a way that they're all lined up. So that this 4 and 14 align with this even. This 0 and 10 align with this even. This 3 and 13 aligns with this odd. 1 and 11, odd. 7, 17, odd. 8, 18, even. 5, 15, odd. So it split it up perfectly in that sense. So what it's doing is it's taking that rectangle and it's splitting it up into a random 70 and 30%. 70%, 30%. It's splitting it up. Now, I'm going to do that with my iris data set. It's called X and Y. So I called it X train, X test, Y train, Y test. If we look at x.shape, x is all of our features, it's 150 rows and 4 columns. If we look at xtrain, it's 112. xtest, if xtrain is 112, how many rows do you expect there to be in xtest? 38. The shape of ytrain is 112. By 1 column. What's the shape of Y test? 38 rows and 1 column. All it did was just split up the 150 data observations into a split. Notice I'm giving it a random state, same thing as the seed. If we all choose the same random state, we all get the same partition. Again, so we all get the same numbers at the end. But if you don't have a random state, we'll all get different answers. Yes?
Would you get the 70-30 split?
When you change the random state, it also changes how much it splits it by. The random state not only changes how much it splits it, but which rows we choose. Okay, so now I have, from our in-sample data, so here's a pop quiz. How many rows were in our in-sample data? How many rows were there? 150 in all the in-sample. How many rows are there in the training set? 112. How many rows are there in the test set? 38. Just split it up. Because here is the proper way of creating a machine learning KNN model in any model. We'll create it, we'll instantiate it, KNN equals K neighbors with neighbors equals 1, the thing that gave us 100% accuracy. We'll fit it to the training predictors and the training response, which is 112 of them, and we'll score it on the remaining values, which now gives us less than 100% accuracy. So now we're getting a better idea. And this is happening because we're pretending that the test set is out of sample. And we're letting the KNN with one neighbor try. And then once it's done trying, we reintroduce the answers back and we compare how well it did. And when we did that, we got a 94.7 accuracy. So here, we'll try with 5 neighbors. Train it on the X train is our training response, training predictors. Y train is our training response, 112, the same ones. And then we'll score on the remaining test again. And we get 97. Okay. We're adding model complexity, which in the article, we have that nice little graph of what happens when you add model complexity, which Catherine, you were hinting at a little bit. Oop, not that one. Here. Blah, blah, blah. In general, as you add model complexity, as you move towards the right on this graph, and by model complexity, I mean 1 neighbor versus 20 neighbors. 1 order polynomial line versus 8-degree polynomial, which is a really curvy thing. When you add model complexity, your bias goes down because you're giving the model more freedom to do what it needs to do to capture everything. The problem is, as you add model complexity, it's very sensitive to change, high variance. This is the bias variance trade-off. The question of, is 1 neighbor better than 50 neighbors, is the bias variance trade-off. Because you'd think that if my model is as smart as possible, it will just be very complex. And that's the connotation that most people in the world have, which data scientists don't. Is that as you add model complexity, your model is inherently smarter. That's not true. As you add complexity, well, think of it this way. As you add complexity to a person, as you add, if you give someone a great amount of book smarts, what do they often lose? What we call street smarts. There's a trade-off between book smarts and street smarts. There's a trade-off between bias and variance. As I add complexity to the model, sure, it's doing a lot better at getting it right, but it's very sensitive to the training data. If I change its data very slightly, this is kind of a weird example, but if someone is very book smart and they learn from logic, if they go out on the streets at 3 in the morning in San Francisco and they don't get mugged, they'll say, okay, if I go out at 3 in the morning in San Francisco, I won't get mugged. Tomorrow they do it again, what happens? They get mugged. They're very sensitive to training data. Now they're very confused, because by logic it happens 50% of the time. So it gets very confusing. Whereas someone with street smarts would say, okay, don't go out in the streets at 3 in the morning. It's a weird example, but it's a trade-off. Where we would like to be is right here. Error, this black curve, depends on 3 things. Bias, variance, and that irreducible noise that we just can't control. Those things that we just will never be able to predict. That's just irreducible noise. But bias and variance we can control with the complexity of our model. We want to adjust the complexity so that bias and variance are in perfect harmony and our error is at its lowest. There is a sweet spot, and scikit-learn helps us find it. So this is when someone was asking, well, what value of k should we choose? This is how we know. We know we have the right k when error is reduced and bias and variance are in harmony. Okay. Down here on line 90, I have a list called out of sample. Out of sample are 2 new flowers that we have not seen yet. When we predict out of sample, it's going to tell us 1 and 0, 1 being the versicolor, 0 being the setosa. It's the same order it's always been. So here's what's going to happen now. If we change the train test split, and I'm changing it by changing the random state. Before it was 4, now it's 1. By changing the random state, I actually get a different training set. Now when I run it with 5 neighbors, here's what I got when I ran it with 5 neighbors with a random state 4.973. When I run it on a different training set, oh my god, I got 100% with 5 neighbors this time. So my error will change based on how I split the data. Which is why cross-validation is very helpful. If we choose several partitions of data and essentially rerun the model for each different potential split and then average the results, we get a better view of what's happening. Because the first time we did it, we got 97%, and then we got 100%. What if we try with a different split and we get 90%? We need to know, on average, what is the error. So here's the syntax for that in scikit-learn. We import something called cross-val score. Cross-val score is a method that computes our cross-validation score. It will actually run the model several times based on however many splits you tell it to do and tell you the average. So I'm going to instantiate a KNN with 1 neighbor. We'll start with 1. And in the 1 line, I'll create a variable called scores. And scores will be equal to the cross-val score of KNN, which is a k nearest neighbors with 1 neighbor, all of my training data, or my predictors, all of my responses. Whoa, I just said don't ever give it all of your in-sample data. Why is this okay now? Why is it okay that I'm giving it all of my predictors and all of my responses? What is cross-validation supposed to do for me?
Change the data.
Partition it in different ways. So when I give it all of my data, its job now is to split it up. I'm not going to split it up. I'm going to give it all of my data, and it's going to split it up for me. How many times? 5. It will take 5 different partitions. It will run KNN with 1 neighbor 5 times. Each time with a different test set and a different training set. All 1 neighbor, but 5 different variations of my in-sample data. And how do I want it to score? Accuracy. So when I run this, after running KNN 5 times with different partitions, it got 0.97, 0.97, 0.93, 0.93, and 1. And to get the average, we throw it into numpy.mean, and on average, KNN with 1 neighbor will yield an accuracy of 96% on average. What if we tried it with 5? KNN, k-neighbors classifier with 5 neighbors. Scores equals cross-val score of a new KNN with 5 neighbors, all of my predictors, all of my responses, 5 times using accuracy. Look how fast it does it too. It did it 5 times. Scores and average them together, 0.97. Ooh, that's better. K and N with one neighbor, on average, has a 96% accuracy. K and N with 5 neighbors, on average, has an accuracy of 97.3%. Cross-validation is the best way to estimate out-of-sample error. Because it takes 5, we can change this number, it takes 5 different partitions. And so essentially it uses 5 different partitions as potential out-of-sample data. So it's pretending to have out-of-sample data 5 times. Now, what if I want to find the best K? Because 1 and 5, what about 28? What about 4? What about 17? Well, one thing we can do, we can make a K range. And K range, if you remember the range, what will K range be? Say it again?
1 to 30 split by 2 of an array.
Right? Yeah, 1, 3, 7. Why did I skip by 2? It was a conscious choice. I decided to skip by 2, but there was a reason. Think of K and N and how K and N works. Why do I only want odd numbers? No ties. Because in K and N, if I have 6 neighbors and 3 are one, 3 are the other, I'll just randomly pick one. I don't want that. I don't want any randomness here. When there's 7 and 4 out of 7 is a setosa, say setosa. It's got to win. Can't be a tie. So I'm not letting it be a tie. Well, I'm reducing the chances of it being a tie by making it all odd numbers. How could it still be a tie? With 9 neighbors, it could be 3 in each column, and therefore it would be a third chance of each, and it would still be random, yes. But when it's even, it's much more likely to be a tie. So I just took out all the even ones and then made it a lot less likely that a tie would occur. So what I'm going to do is I'll have an empty list called scores. And then for each K, for each possible K, I'll create a new K and N with N neighbors K. So I'll try 1, 3, 5, 7, 9, all the way up to 29. And then I'll append to scores, that empty list, the mean of the cross-val score of each K and N with all of my data 5 times with an accuracy. So, how many times will K and N be run? There's 15 numbers in K range, right? For each of those 15, how many times does K and N run? 5. So it's actually running 75 different K and Ns when I run this code. So when I run it, for each of those 15 numbers, it ran it 5 times and then averaged them together. So I end up with the average accuracy for each value of K. You can see here was my 1, here, this 0.97333, that's what we got before when we did it with 5, and here's the rest of them. Now, I love staring at numbers because I'm weird. But graphs are also cool. Here, as model complexity increases, look what the error, or look what the accuracy does. It goes up, and then it goes down. Compare this accuracy to error. Notice how they're complete opposites of each other. Which makes sense. A lower error means higher accuracy. So you can physically see, this is what it looks like when someone makes it very nicely. Here's what it looks like in practice. Our accuracy goes up and then shoots down as model complexity. The number of K is model complexity. And here, as model complexity increases, my error should go down by error going down, accuracy is going up. And then when it gets too complicated, the error starts to increase, the accuracy starts to decrease. This is what it looks like in practice. It won't always be super pretty, like a parabola, but you will very often always see, as model complexity goes up, your metrics will improve until it gets too complicated. It gets low bias, high variance, and your accuracy plummets. Your error goes way up. Yes?
For two opposites with different levels of complexity that can see the same error, which you always want to fix. So you see two.
Ooh, that's a good question. So you're looking at 7 verse 11 here, pretty much, yeah. So the question was, for those who didn't hear it, 7 and 11, K7, K11, appear to have the same exact accuracy, or i.e. same exact error, of both being very low. Which one should we pick? Sanan, not any data scientist, Sanan would say, pick the simpler one. KISS, keep it simple, stupid, right? Keep the simpler one. There are people who would disagree with me, who would say, pick the one that's slightly more complex, because complexity also yields other better things. Like, for example, a lower bias. I personally would pick the simpler model, because, here's why I would do it, inherently, I will probably want to make this model better in 6 months when I have new information. So if I start with a simpler model now, I can add complexity and still feel safe that I'm not getting too complex. If I keep it right here at the brink, and I add just a little bit of complexity, look where the accuracy goes. So I'm tempted to stay towards the left, the simpler model, because it allows me more room for complexity in the future. Does that help?
Yeah.
But there is no textbook answer of you should do this, because it is a debate. Do you guys Patrick, Liam, Ramaj, do you guys have any thoughts on that? Should you choose 7 versus 11? I would choose 7 because it's lower complexity. You guys agree, or do you have another answer?
7. I would also do 7.
That was boring. Well, I guess good, but boring. That's low variance, but yeah. Does this help understand bias variance a little bit more? I hope it does. Because now we're actually seeing the error change, the accuracy change, as model complexity increases. So, let me ask you this. Yes, question?
What about choosing the partitions for cross-validation? Is 5 like a standard, or does that depend?
5 is a standard, yes. But again, there are data scientists who swear by 7 because they're weird. No, it's 5 as a standard, but you generally choose a higher partition when your data set increases. Because when you only have 150 rows, and you split it into 100 different partitions, you're going to have 1 or 2 in each one, right? So the number of times you do a cross-validation is proportionally related to how large your data set is. 5 is a standard, unless you're working with 1 million plus rows of data, then you might want to consider a higher number. And by a higher number, I'm talking like in the teens maybe. But yeah, 5 is standard for most data sets. Yes? No? Maybe so? Hey Sanan, I hate writing for loops. Fine. Scikit-learn answer that question too. Scikit-learn also has another module called grid search. Grid search is not fair, honestly. In my opinion, grid search is just not fair. Grid search, you tell it which parameters you want to tune, and its limits, and it'll just do them all. And you walk away, you grab a muffin and a hot chocolate, and you come back. It's winter in my example. You come back and it's done. It shows you all the results. Grid search is an automated what we just did. I'm going to import grid search. What does CV stand for? Not curriculum vitae, but cross-validation. So it's doing two things at once. It is tuning parameters using cross-validation. So it's trying 1 through 30, or whatever range I give it, and for each one, it's using cross-validation to make sure that we're averaging error, to make sure that high variance, low variance models are captured by doing this. So here's the difference in syntax. KNN equals k-neighbors classifier and then nothing. I don't tell it the number of neighbors even this time. I just say KNN. KNN. Ow, that hurt. I give it the same k range, 1 through 30, with 2, so 1, 3, 5, 7, 9, 11, 13, 15, 17. And then I have to create a dictionary. The dictionary can be filled with as many or as few parameters as I wish to tune. In this example, ParamGrid is a dictionary with one key and one value. The one key, not by coincidence, is exactly the name of the parameter that I want to tune, and neighbors. It has to be exactly the name of the parameter as scikit-learn calls it. How do you know what scikit-learn calls it? The documentation will tell you. The key is the parameter that I want to tune. The value is all of the values I want to try. So in this case, I'm only going to tune one parameter and neighbors, and all the values that I want to try are 1 through 29 with 2 in between. So grid is a grid search object. Grid will be equal to grid search CV, similar to cross-val score. Grid search CV, it will take in my K and N, which is blank. My param grid, which tells it which parameters I want to tune. The number of cross-validations I want, 5, standard. And the scoring I want, accuracy. What are the other scoring? We'll do that in another class. You're still talking. I'm kidding. I was totally, you just happened to be talking as I did that, so I had to go with it. Grid, like a scikit-learn model, is just a blank slate until you give it data. And in fact, if you look at the grid search object, which I know it can be daunting at first, inside of it, we have what it says. CV equals 5, our estimator is a k-neighbors classifier, our n-neighbor is 5, it shows me the param grid, it shows me all the stuff that I just did. Plus many other parameters which I'm not even touching. I'll take that blank grid search, it's like a grid search waiting to happen, and then when I give it fit, it goes. So, how many times, this is actually incorrect math because I'm not very good at math apparently. How many times did it just do K and N? 75. I wrote 150 because I earlier had 131 and then I thought, I'll just do odd numbers.
Yeah, try to put even numbers and just see what happens.
Yeah. Sure, no, a K range is now 1 through 29. Fit it. Done. Here's what it does now. Grid is an object. It has features inside of it. If I do grid.grid scores, it will tell me for each of the parameters I gave it, it gave me the mean, accuracy, and the standard deviation. Standard deviation, as we probably learned at one point, is the square root of variance. So here, we are actually seeing metrics directly correlated to bias and variance. It's showing us this because it actually is important. So, our mean scores, so for each result, we have our, let me make that a little bit smaller. For each of our grid scores, I'm going to take the second element, which happens to be the means. With matplotlib, I will quickly graph the means. And this is all with 1 through 29. But you still see the basic idea of as model complexity increased, our accuracy went up, and then our accuracy went down as the model got too complex. Grid.best score will tell us the best mean. Fair enough. Grid.best params will tell us that 6 actually gave us the best accuracy. The best estimator actually returns back the K&N model. Like the fit scikit-learn K&N model is ready to now predict things with. So grid search is a really simple way of doing a parameter tuning. Now, if I gave it another parameter to tune, for example, accuracy, or the scoring mechanism, and I gave it 2 ways to score it, with 29 of these, or 30 of these, how many times would it run K&N? How many different parameter combinations are there? With 30 neighbors and 2 scorings, how many different combinations are there? 60. How many times does it run for each 60? 5. How many times does K&N run in total? 300. So as you're doing a grid search, take some time to remember arithmetic to make sure you have the sufficient time to wait for something to run 300 times. With K&N, it's not that bad. However, with larger, more complex models, I've seen grid searches take up to 6 hours. I mean, we'll see models that take a couple of seconds to train, but when you tune them across 100 to 150 different variations, that adds up. And one time a student said, I left it on overnight and it still wasn't done grid searching. So just keep in mind when you run a grid search, try to estimate how long you have to wait. Okay, now, excuse me. So we had our mean scores. Two. Yeah. We also had, make it a little bit bigger. The grid will also give us all 5 of the times it ran it. So for each of the neighbors, it'll give us all 5 of them. So just to be aware, the grid search is holding a lot of data about your data. It's giving you all of the trials that you ran, all of the data about them, everything you need to know. So grid search is very daunting at first. I would say that. But it's very useful when you want to try different parameters. Okay, with 15 minutes left, I think that's plenty of time to go over a review of everything that we've done today. I'm sorry, I know. It's the worst teacher in the world. If you look at my Rate My Professor rating, oof, with all 2 people who posted on it. Oh, crap. Don't do it. God damn it. It says I'm laughable. Not that I care. Now. All right. So, what we've done today. The first thing we did was we looked at scikit-learn, which is a new module that we had not seen before. Scikit-learn is a pre-built pre-tested for a very long time machine learning models that have been implemented on many open source data frames, on many proprietary data frames. Scikit-learn is used very, very frequently. We are going to be using scikit-learn to actually use the machine learning models that we learn about. The problem with scikit-learn, if you just Google it on your own, is that it becomes very quickly a black box of knowledge. You throw data in, results come out, and you don't know how to interpret it. So on the same day as we learn scikit-learn, we must also look at the bias variance trade-off. Because inherently, you now all have the knowledge to Google new scikit-learn modules on your own. And in fact, I encourage that. However, what you can also fall into the trap of is trying 20 different models and saying, wow, this thing called whatever this SVM is, seems to always give you really good accuracy. I'm going to always use that. Well, if you don't know what support vector machines, SVMs, are doing behind the scene, and you don't understand bias variance trade-off, and you don't know what grid search is, you don't know how to tune your parameters, you will get stuck using the same model over and over again, and you won't keep getting good results. Okay, now, are there any questions about scikit-learn and what scikit-learn is? Yes?
Is there a model for choosing models?
Yes. Yes, there is. In fact, it's called a human. It's very new. In fact, it's only about 12,000 years old. Model to choose a model is a data scientist. I mean, yeah. If we had a model for choosing models, we'd be out of a job. The data scientist's job is to understand many models and each of their bias variance trade-offs and their applications to very specific problem domains. So part of the optional homework that I gave out was, we're going to be looking at your project first, or your first drafts. However, if you happen to suspect that your problem is some sort of classification, I recommend seeing if you can't implement a KNN on your own data. Try it. Try it. If your model, if your data or your question is not one of classification, that's fine. There is also another data set that I posted that is, not Cora, stop. Ugh. There's another data set I posted that that I think KNN is a very good example for, and it's glass identification. It's given the different chemical compounds of glass, predicting the grade of how bulletproof essentially the glass is based on its chemical compound. And there's data and there's questions on there. As for the resources about what we've done today, there's a lot, but I think they're all very good. This is a 30-second explanation on Quora. It's a written explanation. These are the funniest duo you'll ever see in machine learning. Also, some of the smartest people you'll ever see in machine learning. They're just hilarious. You can tell already how hilarious they are. They have a whole series on statistical learning, and this one specifically is about cross-validation and how do we deal with bias variance. This other one down here is another professor, and I think that this is probably the best 15 minutes on the bias variance trade-off that I've seen. He does it with one example of trying to predict a sine curve. If you had tried to watch this a week ago, it would have been completely nonsensical. But with what you have learned today, this might just be like the 15 minutes that makes it all click. And again, it's all in the resources. All right, as for what's coming up, congratulations on submitting your first homework. Yay. I hope that with the project milestone, you've now all had at least a chance to sit down and think about the different types of data. With the end of this week, comes the new knowledge of the different types of questions that we're allowed to ask. So I think a good way to end the class today is to kind of revisit the idea of the different types of machine learning. So I kind of want to get a sense for what people have been thinking about for their project. So I'm actually going to bring up this graph right here. Okay, so KNN, as we've been using it, what type of problem is KNN solving? Classifications, right? Thank you so much. Classification. Now, as you're all thinking about your data sets, you're all hopefully thinking, what type of question do I want to ask? Maybe I want to predict price, making it a regression. Maybe I want to predict voting habits, which is a classification of only 2 categories. Maybe it's none of those. Maybe I have data and I still fall in this unsupervised realm, which we haven't even talked about yet. What I would like you all to think about, and I'll write it out, it's fine. Think about your data set. Can you put it in terms of regression and classification and some kind of clustering and some kind of dimension reduction? Can you reformat the question to be any one of those 4? If you can't, that's fine. It's not a bad thing, but just so you understand your own data a little bit more. And again, if you think it's mostly classification, try running a KNN on it. Okay, now, we might end class a little bit early. That's fine. Are there any questions about, well, anything we've done today? Probably there are some questions. That's fine. There is no mandatory homework coming up for the next 3 weeks, so relax there. The number one thing I would tell you to do is please keep working on your project. I know it's only the first class, but if you start working hard now, you'll find that you'll have much better results later on. I understand that today was very heavy, and I do apologize if I didn't do the best job of explaining bias variance trade-off in its full capacity, which is why I included these other resources, which may do a better job than I. But that being said, starting Monday, this will become a learning a new machine learning model pretty much every single class. So with this idea of bias, variance, accuracy, metric evaluation, cross-validation, now we're going to be learning many new machine learning models. We now actually have the prerequisite background as data scientists to truly understand linear regression, logistic regression. We'll do an example of an actual problem, clustering, natural language processing, and which each of those new ideas will come. Where's the bias? Where's the variance? How do I decrease the error? What if I perform a cross-validation? These will become inherent questions with each new model that we perform. Okay, let's go ahead and end class here. I will stay after to answer any questions, but have a great night, rest of the week, and I'll see you on Monday. If you haven't done so, please update that Google Doc with your GitHub handle.
Since one page yet.
Okay.
I'm still kind of thinking about stuff. It looks like we don't get to natural language processing until the 20th.